Hello again. Today we're going to be taking another example on energy transformation, but I really need you to watch the previous video if you haven't watched it yet, or you have watched it a long time ago because they are kind of very connected. Today we're going to be talking about conservation of energy in a pendulum. Now, what is a pendulum? Pendulum is a simply fixed mass on a string or a rope that can be swinging freely as seen right here in this picture. So this is a simple pendulum. We will be studying the energy transformation and how the mechanical energy is conserved in this simple pendulum. Now, imagine that you have a pendulum that you raised with your hand to a certain height above the ground. Let's call this location number 1. Now, at point number 1, the object is still in your hand and it is not moving yet, but it is above the ground. So we can say the pendulum is not moving yet, so all the energy is gravitational potential energy. It has no kinetic energy because it's still not moving yet, and it has potential energy because it is above the ground. If you want to remember the mechanical energy at point 1, we know that the mechanical energy is the summation of all forms of potential energy plus the kinetic energy. Now, if we want to study the object at location number 1, we can say that it has no kinetic energy, so all the energy or all the mechanical energy is equal to the potential energy at location number 1. Now, imagine that we let go of this pendulum and we took a picture of this pendulum at location number 2. Now, the object is above the ground. Yes, it's still above the ground, but now it's lower than this point. Now, it's not as high as H. It's lower than H, but it is moving. So it has another form of energy inside it right now. So the pendulum is let go. It starts losing its potential energy and starts gaining kinetic energy. If we want to study the mechanical energy at point 2, we're going to say mechanical energy at point 2 is equal to the potential energy at point 2 plus the kinetic energy at point 2. Now, it is above the ground, so it has potential energy. It is moving, so it has kinetic energy. So the mechanical energy at 2 is equal to potential energy and the kinetic energy. Now, the law of conservation of energy says that mechanical energy is conserved, which means that the mechanical energy at location 1 is going to be equal to the mechanical energy at location 2. In other words, this potential energy, part of it is going to be transformed into kinetic energy. So we will have a less potential energy and we will start gaining kinetic energy. Now, imagine if we took another picture of this pendulum while it was swinging, but when it reached point 3. Now, at point 3, the pendulum has no more gravitational potential energy because it's not above the ground anymore, but it is moving, so it has kinetic energy. And all this potential energy is transformed into kinetic energy. So if I want to calculate the mechanical energy at 3, I'm going to say it's potential energy plus the kinetic energy. And since we have no potential energy, only kinetic energy, so we're going to say the mechanical energy at location 3, it's equal to the kinetic energy at location 3. Again, mechanical energy at 3 is equal to mechanical energy at 2, and it's equal to mechanical energy at 1 because mechanical energy is conserved. Now, we can look at it at point 4. Well, actually, point 4 is very similar to point 2. It is above the ground, so it has potential energy, and it is moving, so it has kinetic energy, so it has both types of energy. And if you want to study its mechanical energy, now we got a hang of it, so we can just say quickly that the mechanical energy at location 4 is equal to the kinetic energy at location 4 plus the potential energy at location 4. And again, mechanical energy at 4 is equal to 3, 2, and 1. Finally, when it reaches point 5. Point 5 is the highest point it will reach. It's the point where the object stops and starts going back into the other direction. So let's say we took a picture of it when it reached point 5 and it stopped. And now it's going to start moving in the other direction. If we want to study this point, we're going to say that the pendulum has now lost all its kinetic energy and gained potential energy again. So the mechanical energy at 5 is going to be simply only potential energy at location 5. In our case, it is gravitational potential energy. And now we will see that the pendulum will reach the same height it started from. Well, actually, this is very important. We must assume that there is no losses due to friction or any other form of losses. Let's say, for example, Now, question if we number put this 3. pendulum in a chamber and we let it swing, theoretically, it's supposed to swing forever because this chamber has no air in it. It is void and there will be no air friction. So it will go perpetually. It will keep on swinging forever because the energy is transforming from potential to kinetic, then potential, then to kinetic, and so forth. So again, mechanical energy is conserved. So the mechanical energy at 5 is equal to 4 and 3 and 2 and 1. Now let's try to solve this very small, simple example. Say that the value of h is 1.5 meters, so the pendulum is 1.5 meter above the ground and it has a mass of 0.1 kilograms. It's asking me to find the potential energy at location 1. Well, actually, it's pretty easy because we know the potential energy is equal to mgh. In our case, the mass is 0.1, and g is 9.8, and the height is equal to 1.5. So this will give us an answer of 1.47 joules. Pretty straightforward. Now it's asking me to calculate the kinetic energy at 3. Well, this is kind of difficult because I do not have any velocity. You will start thinking like this. You're going to say that the kinetic energy is equal to half mv squared, but I don't have the velocity. Yes, I have the mass, but I do not have the velocity. So this equation will not help me. So let's think out of the box. Remember that mechanical energy is conserved. And I know that the mechanical energy here at location 1, as we found it before, is going to be equal to the potential energy at location 1. And the mechanical energy at location 3 is going to be equal to the kinetic energy at location 3. And I know that mechanical energy at 3 is equal to mechanical energy at 1. So I'm going to say that the mechanical energy at 3 is equal to the mechanical energy at 1. And I know that the mechanical energy at 1 is equal to the potential energy. So mechanical energy at 3 is equal to the kinetic energy. So kinetic energy at 3 is equal to the potential energy at 1. Now, we already found this. We know that the potential energy at 3 is equal to 1.47. So this means that the kinetic energy, we can replace this with 1.47 joules. So it's straightforward. We can just say that all the energy transformed from potential energy to kinetic energy. If 2 was midway between 1 and 3, find the potential energy and the kinetic energy. Okay, we know at 2 right here, the mechanical energy is going to have two types of energy. We will have potential energy at 2, and we will have kinetic energy at 2. Okay, it's asking me to find the potential energy and the kinetic energy, but it told me that 2 is midway between 1 and 3. So I can assume that the height here, it's not 1.5, it's going to be 0.75. So finding the potential energy will be very easy. I can say that the potential energy at location 2 is simply equal to mgh, which is equal to the mass, which is 0.1 multiplied by 9.8 multiplied by 0.75. This will give me an answer equal to 0.035 joules. So finding the potential energy was very easy. Now I need the kinetic energy. Again, I do not have a velocity. So let's think about the law of conservation of energy and that the mechanical energy is equal everywhere. Mechanical energy at 2, we already found out the mechanical energy at 2 is equal to the potential energy at 2 plus the kinetic energy at 2. So I already found the potential energy at 2, which is equal to 0.735. So I'm going to say this is equal to 0.735 plus the kinetic energy at 2, which I do not know. Now I have two unknowns. I have the mechanical energy at 2 that is unknown and the kinetic energy at 2 that is unknown. But I know that the mechanical energy is conserved. This means that the mechanical energy at 1 and 2 and 3 and 4 and 5 and etc. will be always the same. So I can replace the mechanical energy at 2 here with the mechanical energy at 1. And we already found that the mechanical energy at 1 is equal to this potential energy, which is equal to 1.47. So I can say that mechanical energy at 2 is equal to 1.47. This is equal to 0.735 plus the kinetic energy at location 2. Simply, I can say that the kinetic energy at location 2, I will subtract 0.735 from both sides, and I will get that the kinetic energy is now equal to 0.735 joules. Now, you can say that the kinetic energy here is equal to the potential energy. Well, exactly. The whole idea of solving this example was to get to this conclusion, which is since the pendulum is halfway between 0.1 and 0.3, this means that half of the potential energy will be transformed into kinetic energy. So I found the potential energy and I found the kinetic energy at location 2 using the law of conservation of energy. So next time you won't have to do this calculations on these numbers. You can just go straight forward and answer that, since it's halfway. Half of the energy will be potential and half of the energy will be kinetic. Actually, if you were asked to find the velocity of the object at point 2, we know that the kinetic energy is equal to half mv squared, and we have the kinetic energy, it's 0.735, and we have the mass, so we can simply find the velocity. I hope now things are a little bit more clear. Now, since we already opened the topic of pendulums, let's might as well mention something called the time period. The time period is the time taken for the pendulum to make a full swing. In other words, starting from point 1, reaching to point 5, then it went back to point 1. This is one full swing. How much time did it take it to do one full swing? Well, this is called the time period. The time period can be found simply using this equation. T is equal to 2 pi square root of L over G. Now, T is the time period, and it will be found in seconds. 2 pi, 2 is a constant, and pi is also a constant equal to 3.14. L is the length of the pendulum. Or in other words, the length of the string of the pendulum from this point here to this point here. And finally, G is the gravitational acceleration. Well, actually, this means that if I have two pendulums, these two pendulums had the same length and different masses, they will have the same time period. In other words, they will be moving at the same speed. Well, this takes us back to the assumption when we said when we throw two objects, one is large and one is small, in a vacuum, they will both reach the ground at the same time. Well, this is very similar to it. Two pendulums with different masses neglecting air friction, as long as they have the same string length, this means that they will have the same speed while swinging, or in other words, they will have the same time period. Now we will introduce another term called frequency. Well, the frequency is a portion or the portion of a swing a pendulum can do in 1 second. In other words, if a pendulum can do 5 swings in 1 second, we can say that the frequency is 5. If it can do only half a swing in each second, we're going to say that the frequency is equal to half. And how can we find the frequency? Well, the frequency is 1 over the time period. And the unit of frequency is hertz, or 1 over second. And we already know that the time period's unit is seconds. So we introduced two other terms, which are frequency and time period. Stay tuned for the next video, where we will be introducing more types of energy transformations that are very likely to be seen in the exam. So stay tuned.